Hello. Today we're going to talk about Chapter 7, Linear Regression. All right, so what is linear regression? Well, let's go back to correlation from the last chapter. The correlation right here would say that the association between these two variables is fairly strong, but it doesn't tell us what the line is. It doesn't help us predict anything or estimate. So we use a linear model is the equation of a straight line through that data. Okay, so if we want to model it, we call it a linear model. All right? So how do we make that best line? Okay, so we want to find a line that's close to all the points. Okay, so some points obviously are going to have to be above it, some are below it. Okay, that difference between the point on the line and the point from our data is called the residual. All right, so notice that the predicted value, we changed what the y looks like. It has a little caret on top. All right, that is called a y-hat. Okay, so yes, y-hats are the fancy predicted. Yes, that's what I would estimate. At least that's how I hear it in my head. That's how I remember y-hat. Okay, it's the predicted value. Y is your true value, so from your actual data set. So yeah, that's just Y. Okay? All right. Let's talk about those residuals. Okay? The residual tells you how far off you are off the model's prediction is. Words, man. Okay, so residual is you take your observed value, so Y, and you subtract your predicted value, which is y-hat. Okay, so if I give you a negative residual, so a negative number, that means that our observed value is, that our predicted value is too big. Okay, because if it's negative, it's easier just to look at the data. Okay, so here we're doing y minus y-hat. This would be a negative residual. But if here we would do this y minus this y-hat, and that would be a positive residual. Okay, so kind of think about it there. Okay, may seem backwards, but this is how it is. All right, I like to think about the visual, or visualize the graph. Okay, so what do we do with these residuals? Because we can't make the line fit by just adding up all those residuals, right? Because the positive and the negatives would all just cancel each other out, so we'd be stuck with 0, okay? The average of your residuals should be 0, right? We want it all close to the line. So what did we do when we did standard deviation? We squared it. Right? We squared the residual. So we squared the differences for standard deviation, so that's what we're doing here. So the line of best fit, okay, so the line of best fit, the best line for that data, okay, is the line which the sum of those squared residuals is the smallest. We want the smallest amount, okay, the least squares lines. Okay, so the line of best fit is the least squares line. That's the same thing, okay, they're synonyms. Okay. Okay, so how do we model that relationship, right? How do we describe that linear model? Well, hopefully the obvious thing to say is a line. So you know that a line is just y equals mx plus b. Okay, well, here we're just going to think of just a basic line, y equals mx. Okay. So let's take that and consider our data. Okay, so think about what we're putting here. The x would be from our data set, but the y that would come out would be our predicted value, right? So we're going to start with our x putting in and our y putting out, but remember we have z. Why did we put a z? We standardize the values, right? When we standardize it, we're looking at the z-scores. So take your z-scores of x and your z-scores of y, and what you put in, okay, is from your data set, and what you get out is what you predict. Okay, that's what a model is doing. It's giving you predictions. Okay, so that helped those, but now let's think about what M would be. Okay, so M in this case would be our R. Okay, our correlation. That's what we learned in chapter 6. Okay, so if that totally confused you, okay, maybe it might make more sense to think of it in a sentence form. So, in general, moving any number of standard deviations in x, so any number of standard deviations of x, is going to move that number, r times that number of standard deviations in y. Okay, so if we go over one standard deviation in x, we're going to go up r standard deviations in y hat. Okay, this is what our slope is. Up 1 over 1, or I guess we're going to go over 1, up 1. So over 1 standard deviation in x, up r times that standard deviations in y hat. Okay, that's what this means. Okay, so let's actually put it to something that makes sense. So we've got the scatter plot of house price versus house size. Okay, it shows the relationship is straight with only moderate scatter and no outliers. Great, wonderful, everything we want. The correlation is 0.77. So you go to open house and find that the house is 1 standard deviation above the mean in size. So what would you guess about its price? Okay, so if the house is 1 standard deviation, then we should expect the y to go r times that. So r is 0.77 times 1 is 0.77 standard deviations above the mean. So if the house, that's how we can deal with correlation, right? You're thinking of it in, in a linear format. So we're putting in house size, okay, and times the correlation is going to give, is going to have the output of the price. So if we went 1 standard deviation in size, then we're going to go r times that in standard deviation in price. Okay, so now if we read that it's going 2 standard deviations below, well, we do 2 times that. So 2 times 0.77 gets us 1.54 standard deviations below the mean. Okay, so think about this. A friend tells you about a house whose size in square meters is 1.5 standard deviations above the mean. So what would you guess about its size in square feet? So if I change it from meters to feet, what does that do to the correlation? Hopefully you know, okay, that it doesn't matter, okay? Units don't affect the correlation. So here it's going to still be 1.5 standard deviations. Okay? So let's think about that for a minute. If you think, if x is 2 standard deviations above its mean, well, we're not ever going to guess more than 2 standard deviations away for y, because r can't be bigger than 1. Okay? So each predicted y value tends to be closer to the mean. Okay? So even though x is 2 standard deviations, y is not going to be that far away from its mean. Okay? So what that means is regression to the mean. Okay, it's a regression line because you're going closer to the y values. Okay. Yeah, I really don't know how any other way to explain it. I think your book does a really good job there. Got questions? We can talk about it more in class. And of course, since these regressions rely so heavily on correlation, we have to do the same conditions. Okay, make sure that they're quantitative variables, it's a straight enough condition, and you don't have any outliers. That's the only time we can use these linear models. So let's talk about writing our regression line. Okay, our line of best fit. Okay, so our regression line is y equals a plus bx, very similar to what you've seen, y equals mx plus b, where we have our y-intercept and our slope. Okay, so look at how we get our y-intercept. Okay, so let's first start with the y-intercept of trying to find our regression line. Okay, so first thing, I don't know why this wrote so dark or so light, but this is supposed to have a bar on top of it. That represents the mean. Okay, so the mean of y minus b times the mean of x's. Okay, the y-intercept isn't as useful in real data, okay, because usually it doesn't really make sense. Okay, the year 0, a baby born weighing 0 grams, that doesn't really make sense. Okay, so really look at your data set to determine whether or not y-intercept would be useful thing to mention. Okay, because it really it's usually not very meaningful. Okay, and you'll see that. All right, the slope, how we get that, we've talked about that. That is the your correlation value. Okay, but there's a little bit more to it. We want to also include our standard deviation of y and our standard deviation of x, right? Change in y over your change in x. So your standard deviation of y over your standard deviation of x. Okay, so changing the units of your slope doesn't change the correlation, okay, but it does affect the slope. I don't know if I said that right. Okay, so changing the units of x and y changes the standard deviation. So that's why it's affecting the slope. So your correlation doesn't change from your units, but your slope is. Okay? So there's always a ratio, all right, and it has to do with your units. So let's start with an example. Okay, let's go back to the price and house size. Okay, get my pen. All right, so what does the slope of 94.454 mean? Okay, so that's your slope. Look and notice what x is and what your y is. X is your size and y is your price. Okay, so that helps in, once you identify your x and y, that'll help you with your interpretation. Okay, so what does the slope mean? Well, remember, that's your standard deviations, right? So one change in size is going to do this much change in one price. So an increase in home size of 1,000 square feet is associated with an increase in price of 94,454 on average. Okay, so why did I say 1,000 square feet? Oh, because that's what house size is in thousands of square feet. So in 1 unit of size, so in 1,000 square feet, associated with that price change on average. So what are the units of slope? Well, slope is y over x, so price over size. So units are thousands of dollars per 1,000 square feet. All right, your house is 2,000 square feet bigger than your neighbor's, so how much more do you expect it to be worth? All right, well, you plug it in. Okay, so if we plug it in, we expect the price to be above this on average. Okay? So that would be your size. You're plugging that in. Okay. Is the y-intercept meaningful? Well, think about it. To get the y-intercept, the size would have to be, pretty sure no one wants a house with 0 square feet. Okay? So hopefully this makes a little more sense. So now that we know what those residuals are, let's talk about what we can do with them. Okay? A residual, notice what the variable it uses. It's E. Well, 1 because R was already taken for correlation, but E is basically short for error. Okay? So residual is kind of synonymous to the word error, so standard error. All right, so we look at the residuals, and that's how we know how and where the model is going to fail. So after we fit a regression model, we plot the residuals to make sure. Okay? Usually we're okay, but sometimes the residuals, if we plot the residuals, we find something weird. So what is normal and what's weird? This is normal. Nothing about that is interesting at all. Nothing stands out. This one is actually kind of interesting. It's got this neat little curve. Okay? We don't like it. That tells us something's wrong. Here, I don't like this at all. It starts off okay. Well, hold on. It starts off over here okay, but then it changes, right? We don't like this change. Not good. Go back and look at your model. See if you can manipulate something. Okay? Also here, we should not be having this happen. Okay? This is interesting. We don't like interesting when it comes to residuals. Residuals are just verifying that, yeah, this is linear. You're good. Okay? That's what we want. Okay. Let's see. Yeah, next one. So let's do an example. So going, of course, back to the size and price. Here we have our linear model. Now let's think about the residuals. If you were going to buy a home with a negative or positive residual, what are we looking for? Okay, well, think about the residual. It's y minus y hat. So our value minus our predicted price. Okay, so think about this. Our value, that's actually on market, okay, minus our predicted price. Do we want that to be positive or negative when we're buying a home? Well, I want my predicted price to be higher, right? I want to save some money. So if I want the predicted price to be higher, that's a negative residual. Okay? All right, so now we plan to look for a home for about 3,000 square feet. How much should we expect to pay? That's a prediction, so we're going to plug it in here. We plug that in, we get out 280,000. Okay, that's what we expect to buy. But we find a home that's selling for 300,000. Okay. Well, what's the residual? Again, value minus predicted value. So 19,755. It's positive. Positive and negative make a big difference here. All right, so no partial credits here for getting positive and negative mixed up. Okay, you gotta know. All right. All right, so after we find that the residuals show nothing interesting, we look to see how big they are, right? Because if they're really far away from our prediction lines, then they're really not useful. Okay, so I want them to be close to, I want to be close to 0, right? Since their mean is always 0, we want to see how much they vary. Oh, I think I just turned myself around again. Okay, so here, it's a good idea to make a histogram of your residuals just to double check it, right? It's another visual check that you're on the right path. Okay, so you want to see a unimodal symmetric histogram, all right, that we can apply the 68, 95, 99.7 rule. Oh, yeah, the bell curve. Yes, that. Okay, so that will tell us, we can apply that to the data. Then we'll see that our residual should be within 2 standard deviations of that mean of 0. So again, if we do a histogram of your residuals, most of it should be within 2 standard deviations of that mean. Okay? Of its data, of that residual stuff. I hope I'm making sense. Okay. All right. We can also check another check, because that's all we do in statistics, is we can check the appropriateness by looking at R squared value. We read it as R squared. Don't say R2, okay? It's R squared value. So this tells us the percent of our Y variation that is determined by variation in the X variable. It's a mouthful. It's one of those things, the more you use this vocab, the easier it becomes, okay? So let me use it in words, okay? A real world example. So we predict maximum wind speed in hurricanes based on the storm's central pressure. It gave us an R squared at 77.3%. So what does that say about our model? Okay, so in words, it indicates that 77.3% of the variation in wind speed can be accounted for by the hurricane's central pressure. We're saying, yeah, about 77.3% of that change is because of that central pressure. Other factors, such as temperature, whether the storm is over water or land, may explain some of the remaining variation. The remaining 22.7%. Okay? So it's just telling us how much it kind of depends on each other. Okay, or not depends, how much that accounts for. All right, let's keep doing examples. So back to our just checking. Okay, price per size, or versus size, whatever. The R squared value is reported as 59.5%, and the standard deviation of the residuals is 53.79. Great. What does the R squared value mean about the relationship of price and size? Okay, got your idea? The difference in size of houses account for about 59.5% of the variation in the house prices. Okay, so the differences in X account for R squared percent of the variation in Y. Okay. Number 12, is the correlation of price and size positive or negative? How do you know? Well, it's positive. The correlation and the slope have the same sign, of course. All right, hopefully that's what you thought of. Okay. If we measure house size in square meters instead, would R squared change? Would the slope of the line change? So we're changing the units. What does the units change? There we go. R squared would not change, so your correlation R is not affected, but your slope would. Slope depends on units, correlation doesn't. All right, so you find that your house in Saratoga is worth $50,000 more than the model predicts. So should you be very surprised as well as pleased? Well, seeing how the way I said it, okay, as exciting as it is, it's not really, it's kind of obvious, all right? Think about it. The standard deviation is 53.79. That's in thousands of dollars, okay? We should not be surprised by any residual smaller than 2 standard deviations. Okay, so it had to be more than, 107,000? Okay, Think about that. All right, as exciting as it may sound to you, it may not be to the data. Okay? All right, I get this one a lot. All right, what should R squared be? Well, I don't know, it's percentage, so I guess between 0 and 100. Okay, but what's a good R squared value? Whew, didn't fix that one. Okay, it depends. Depends on your data, okay? There are some data sets where they want they want 99.9% to be R squared. Then there's some data where they're like, we'll settle for 60. Okay, so there's no value that automatically determines that regression is good. It depends on your data. Okay, ideally we'd like it to be 100%, but that's unrealistic. That would be all of our data lining up perfectly on our model. That's never going to happen. Okay? You know, it's real life. Things change. Things vary. Okay, so they like to throw these in there. These are the statistical output from computer calculations. Okay, I don't know why they always use these. Well, probably because they're more useful than a graphing calculator. Okay, once you start getting into more and more data, huge data sets, you're going to use Excel spreadsheets and things like that, computer programs, and they're going to spit out the data like this. So if you ever see this and you're looking for your model, why didn't I put this up before with the regression, the linear stuff? Anyway, doesn't matter. Look for constant and coefficient. That's going to help you find your numbers. Okay, so the number after constant is the y-intercept. The number next to revision time in this one would be considered the slope. Okay, so then they would write it exam score versus revision time, y-intercept plus your slope times revision time. Okay, so just knowing how to read that data. Really should have put that up there with the other stuff, but that's okay. It does give you your R squared value. So see, you can see that there. Anyway, so before you do anything, all right, before you start your linear models, okay, before you start finding out what the slope is and y-intercept and all that stuff, you need to make sure that the quantitative variable condition is met. Okay, if it's categorical, it doesn't make sense, stop what you're doing. Then from there, do your scatter plot of y against x. Check your straight enough condition, your outlier condition. Does the plot thicken condition? So does the spread of the data around the generally straight relationship seem to be consistent for all values of x? Like you wouldn't want to have here. So here's your line. You wouldn't want to have a bunch of dots here and then suddenly be all over here. Okay, you wouldn't want that. Okay, so does the plot thicken? That's what they're talking about. Okay, I don't know why I erased that. Whatever. All right, so after fitting the regression model, so after you get your linear model, you make a plot of the residuals and you look for any bends that would violate the straight enough condition, any outliers, any change in the vertical spread. Okay, so similar to that, does the plot thicken? You want to check to see if anything stands out, right? When you plot the residuals, you're looking for nothing. You want nothing to show up. All right, so statistics does not come out of nowhere, all right? It's always based on data. It always comes from something. So if something surprises you and you're like, wow, I did not expect that, then you either learned something new about this world or your analysis is wrong, okay? So you've got to determine what you just did. So how do we know if it's surprising or not? So how do we know if that correlation is good, if our slope is good, if those things are good? You can check the extremes, okay? So if there was what was the model in the book? Something about sugar. The correlation between sugar and calorie intake was 2.5 grams. So, 2.5 grams of sugar for every 100 calories. Well, do the extremes. Is 0.25 grams of sugar for every calorie make more sense, or 250 grams of sugar for every 100 calories? That's what they mean by multiply, divide by 10. You're checking to see if, does it seem plausible? Is it reasonable? Okay. Always look at your data. All right. So some stuff that can go wrong. Okay. Don't put a straight line on a nonlinear relationship. You could have great R's, great correlation, great R squared. Oh, it looks perfect. It is 99%. And it's not a linear relationship. It's useless. Means nothing. Beware of your outliers. Okay? You can't have those. They will mess you up. All right? Also, causation. All right? Correlation does not equal causation. X does not cause Y. Do not say that. Just because there's a good linear model does not mean it causes it. Okay? All we can say is that there is a relationship. There's a correlation there. And do not choose a model based on R squared alone. R squared is not going to help you pick the best model. Okay? Don't invert the regression. The best way to explain this is really with that comic. I really love this comic. All right, if you don't understand it, let me explain. So this guy without the hat says that cell phones cause cancer. Or said that found no evidence that cell phones cause cancer. Great. The guy with the hat was like, nope, flip it around. He thinks cancer causes cell phones because of this data he got. Look at cancer kept increasing, and then when it hits its max, well, suddenly cell phones are around, and cell phones keep increasing. Okay? Don't flip things around. Okay? Don't invert it. Don't twist it. Don't turn it around. Okay? Just because it doesn't show a relationship there doesn't mean you can flip it around. I hope that makes sense. If not, you know where to find me.